All right, let's move on to some material. So it is, in case you were just starting to watch the video, it's April 5th, and today we're going to be talking about um, moments of inertia, second moment of inertia, kind of the physical properties that we can describe with multivariable integration. So if you guys remember, maybe from high school physics, I'm sure you've probably taken physics by now for Calc 3 if you had to take physics. Moment, we have this, basically you apply a force from a certain distance about an axis, and then you describe it as a moment about that axis. So, we could say in 3D, if we're looking at this, if our wrench is right here, right? Terrible wrench, but I'm doing my best. So if our wrench is right there, and this is the X, Y, and Z axes, and if we do a force, excuse me, oh, my computer freaked out. If we do a force down Z, then we have a moment about the y-axis. That's how that works. And you can see that described here. So this would be the y-axis looking into the picture. We saw in lecture, as you guys remember, we have a couple definitions. There's mx and my, so we can talk about this in terms of two integrals or three integrals, depending on what we're talking about. So we have a moment about an axis. When it comes to Calc 3, now I know if you took physics or maybe even statics or dynamics and stuff like that, we can pick an arbitrary axis and use a lot of trigonometry. But in Calc 3, what we're going to talk about is pretty simple. You can just have integration y, and then this will be times the density of xy dA. Now this density function, it could be related to mass, and usually it will be, because in Calc 3 we don't stray away from there, but density could be anything, right? That could be like the density of a pressure load. It could be the density of really any sort of load. So right now we're just going to call it mass because that's easy. My will be the region, it'll be x times the density function, dA. And this is pretty easy to remember because if you have your x right here, then you just switch the y. Easy enough. And it's easy enough to remember where here's your force, right? This is your density of xy, and then this is your y. So it's pretty easy to remember. Or this is your x, even, depending on what axis you're taking about. But if you're taking about the x-axis, then of course you have to multiply by the y distance. And the same thing for x, kind of how we talked about in lecture. What about for 3D? I'm going to challenge you guys to use your notes. See if you can fill this in, or if you can fill it in from memory. I'll give you about 30 seconds and see if you can recollect it. And I'll set a timer and go for it. All right, let's see how you did. So mxy, we have as the triple integral, right? It's a surface, so we write a little s there. Z delta xyz over r volume. Okay. mxz, if you guys are starting to detect a pattern, it's whatever one is missing, right? So we're missing a y right here. So if we miss a y right there, that means it's going to be a y right there. Delta xyz dv. And then the same, we're missing an x. I guess the x would go in front of here. We're missing an x. So we would have an x right here. Okay, cool. So now that we kind of know what we're talking about, let's look at a problem. Find my for a density with a function of a density function right here. So we saw this in the lecture on Friday. If you guys watched Butler's lecture, I'm going to challenge you guys to go for this right away. Try not to use your notes if you don't have to. Remember that my is equal to the region, and because we're missing an x, it's going to be an x times the density function, dA. All right. I'll give you guys about 2 or 3 minutes to go at this one. See if you can do it without using your notes, but if you need to reference your notes, I guess note review is always a great skill to practice, and I'll get back to you in about 3 minutes. Good luck. All right, so that was about 3 minutes. Let's take a look at what you would have done to solve this problem. So first, like any multivariable calc problem, when we have to write domains, it's easiest to first start by drawing the bounds. So let's draw the bounds. We've got an x and a y. So we've got two functions, right? It says x is less than or equal to, or y squared is less than or equal to x. So let's draw that guy like we might have before. We've definitely seen this function before. X is less than or equal to 1 right here. So that's x is equal to 1. And we've got x is equal to y squared. And we're obviously concerned with this domain right here. All right, very cool. So we can draw those bounds and write those bounds pretty easily. So we have m of y is equal to our region times x times the density function, xy squared. And then we've got dx dy, or dy dx. I guess we could decide whichever one we want to. Try looking at this problem and figuring out which way you think would be better to start with. Think about it to yourself, and if you had to ask me, I would say dx dy is probably better, because this inner bound has to be a line of some sort, as you remember. So that inner bound, and we already have a line written out, which on the y is y squared, and then we go x is equal to 1, which I think would work pretty well. Then we do know that our y, we go from 0 to 1, or from -1 to 1, so we'll put that there for our bounds. And now all we have to do is just solve this guy to get our moment in the y. So let's simplify it a little bit. Oh, sorry, my brain is moving too fast. This will be a 1 and this will be y squared. So we'll have x squared y squared dx dy. And hopefully you did your best at solving that guy out. If you did, you would get that my is equal to 4 over 27. Very cool. Okay, so we found the moment of inertia about the y-axis, which is really cool. Let's move on. So what does x bar and y bar represent, and how are they solved for? And how can they be used to find the center of mass? So, like we talked about, the moment y is the moment about the y-axis. That's what's kind of big. So to find y bar, what we do is we take that moment of the y about the y-axis, and we basically take the average of it by dividing it by the mass, kind of like we talked about. Oh, excuse me, this would be x bar. So x bar would be equal to my over m, which means y bar is equal to mx over m. And what x bar and y bar are they're the lines of basically symmetry across this shape when it comes to the mass. So it means that it's basically, if you were to take like a set that mass, that big shape, on the edge of a table, right on that x bar line, or right on that y bar line, it would be perfectly balanced where it wouldn't tip one way or the other. So you would have, like, say, like your x bar is right here, and then your y bar is right here. So of course your center of mass is just going to be where the two intersect. So your center of mass is equal to x bar and y bar. So sometimes, like we talked about in lecture, you can find x bar or y bar pretty easily if the shape is symmetric and if the density is symmetric. So like what we talked about, if we have a line right here, if we see that the shape is symmetric, we can automatically say, okay, maybe the mass will be symmetric. And what we have to do is go and look at the density function and see if that is symmetric. So what we're thinking about first, so what we care about first is our y bar. Let's try that first, because that might be symmetric. As you can see, and I'll get rid of all of this, we are symmetric across the x-axis, which is great. If we're symmetric across the x-axis, how about our density function? Density xy is equal to xy squared. And some easy way to test this usually is see what the density is. If we keep x constant, let's just try x is equal to 1. Let's try a density of 1, and we'll get obviously 1. Now let's try a density on the exact opposite side of the x-axis, which is -1, right? So we're testing like here and here. Well, I guess technically we're testing here and here, but that's a technicality. We're just testing either side of that x-axis, keeping x the same, and we get 1 again, because that y squared. And we could try the same thing for like 1, 2, which would be, it would come out to 4, and the same thing would happen if we did negative 2. So we know it's symmetric across that x-axis, so our y bar is just 0. Our y bar is just the x-axis. So y bar is equal to 0, because it's symmetric. And now if we look at x bar, we just found our m of y, and our m we actually found in a different problem. If you remember, we've seen this problem before, and it's just 4 over 21 like we talked about in lecture. So that means our my becomes 4 over 27 divided by 4 over 21, and that's our center, that's our x bar. So then our center of mass just becomes our x bar, which is 4 over 27 divided by 4 over 21, comma, 0. Boom. So we got that answer. Center of mass problems are fun. Okay, so we've seen this one in lecture 2. Set up the integrals to find z bar from basically this box region. This region is just a big old cube. Remember, it's a bunch of lines going on, where this density function is right there. And all I really care about is you guys setting this up, because solving it isn't too big of a deal. But we want to find z bar. So you need to set up 2 different integrals. I'll let you guys try to figure out what those are. Refer to your notes if you need to. I'll give you guys about 3 more minutes, and we'll come back then and see how you guys did. All right, coming back for z bar, remember from above we have its mxy over m. So we're going to need mxy, and we're going to need the mass. So maybe I'll do 2 different colors for that. So let's do mxy first. So we'd have our surface. We'd have, because it's xy, we're missing a z, easy enough, z, times our density function, which is x squared z plus y squared z squared. Cool. And then we've got our dv. We'd have to set the bounds for this. So we'd have, and let's just combine all the terms while we can, plus y squared z cubed. So we'd have to do a dz dy dx, or dx dy zz, or something. And of course, we're not going to solve this, so it's not too big of a deal. But it'd be easy if we just cognitively think about what we want to do. I see a 0 to 2 for the z, and I kind of want to start with that 0. So let's just start with that 0. So let's put a dz on the inside. And then after we do the 0, I guess it doesn't really matter, so then we can just do dy dx. It's fine with me. So then we'd have to make our bounds the same thing, 0 to 2, and then -1 to 1 for both of the rest of them. Cool. for the mass, if we remember our mass equation, our mass is just integrating the density over the volume. So it'd be x squared z plus y squared z squared. Let's do the same thing, dz, dy, dx. And we'll go from 0, 1, negative 1, 1, 1, 2. Cool. So we set up the integrals. Now we technically have to solve both those integrals, and then to get z bar, we just put mxy over m. Simple enough. All right, cool. Let's move on. A quiz problem. All right, we've been looking at this quiz problem for freaking ever, and we're finally going to solve it to its entirety, which is exciting. So find the mass and the center mass of the region consisting of the triangle with the vertices. We've seen this before. We've drawn the picture a few times. And remember that the mass is 2 over 3 because we've solved that. So yeah, now that you guys know how to do this, I'm going to let you guys try and go for it. Remember your symmetry, right? Does your density change across the x-axis? Maybe it doesn't. Is the shape symmetrical across the x-axis? Maybe. What does that mean for your y bar and your x bar? Yeah, I'll give you guys about 4 minutes, maybe 3 or 4 minutes to go for this. Give it your best shot. This is a great problem, and we'll come back. Good luck. All right, so let's take it back and see how you guys did. So remember we've drawn the shape a few times. It's just an inverted triangle. We know that this line is x is equal to y. This line over here, y is equal to x. Okay, so our density function is, let's draw it with green, is equal to y. That's all it is. So it only changes when you change in the y. It doesn't change at all in the x. And you can see that our shape is symmetric about the y-axis, which means that our x bar is just 0. So our x bar is right here. Oh, I erased it. Okay, that's x bar. Cool. Okay, so now we need y bar. You can kind of guess it's probably going to be like somewhere up here maybe. It'll probably be around there. We can just look at it and guess, seeing that it gets more dense as y increases. But to do that, we need to find the moment of inertia for x, because remember that y bar is equal to mx over m. So mx is equal to, remember it's a y on the inside for the region, times the density function, dA. So we'll do y times the density function, which is just another y. We can do dx or dy first. Maybe let's just do dx, dy. If we did dy, remember we would have to have two separate integrals, because if we do dy, we'd be slicing it vertically. And we don't want to do that. We want to slice it horizontally, so that we only need one integral to solve. So our dx, we're going to go from y is equal to, and this should be negative x, or this should be x is equal to negative y, or the other way around. So we'll have a negative y on this guy, we'll have a positive y. And then for our y, we're going from 0 to 1. We've done that before. Okay, so now we're just solving this integral 0 to 1, negative y to y of y squared dx dy. So hopefully if you guys set this up, this was kind of the big part that you would need to get. And now we just solve it. We get 0 to 1. Of course, with respect to x, so it'd be xy squared, negative y to y dy. So then we'll get 0 to 1, some tricky stuff here, y cubed minus, and then it'd be, well, I like to do this. I like to keep my brackets for each side of the evaluation we do. So it'd be y cubed minus, time for our second brackets. We'd plug negative y in, so it'd be negative y cubed, and evaluate that. Okay, so we've got that, and then we just have a dy there. So we would have 0 to 1 of 2y cubed dy. So bring that over there. We'll get, let's think about it. What is that? 1/2 y to the 4th from 0 to 1. So we'll get 1/2 is equal to our my, or mx, excuse me. Cool. So mx is equal to 1/2. We already know that the mass is 2/3. So we can say that our center of mass, I'll do it in a different color. Remember, it's equal to x bar, y bar. We found that our x bar is 0. And our y bar is just mx over m, which would be 1/2 divided by 2/3, which is also just 3/4, I think. Yeah, 3/4. Boom. Center of mass. Yeah, we solved that problem. We've been around that for a while, so it feels good to solve that, doesn't it? Okay, cool. Center of mass problems. We'll definitely get into some more complicated ones as the semester goes on, especially as exams come up. But yeah, we can also find this one. Find the center of mass of a thin rectangular plate cut from the first quadrant by the lines. So we've done this together in our sessions. And I can pull up the work for it here that we've already completed, so we kind of know where we're at. But the mass is equal to 27, if we look at it. It's a thin rectangular plate in the first quadrant, so the lines x is equal to 6, and y is equal to 1. So it's really just like a big rectangle like this. This is 6, 0. This is like 6, 1. this is 1, comma 0, and this is 0, comma 0. And it says if its density is given by that density function, find the center of mass. So we're going to need the mx and the my, of course. And it get a little complicated, but we can do that. So we'll need mx is equal to, remember, it's going to be y times the density function dA. Excuse me, we don't need a triple integral, we just need a double integral. The region dA. And my is going to equal x dA. And we can solve all of this. Let's see if you guys can solve just for the mx. Go ahead and go for it. You'll have to set your bounds and everything. And then I'll give you the my just so we don't run out of time. And yeah, I'll give you guys about 3 or 4 minutes to solve for the mx. Good luck and have fun. All right, sweet. Let's check it out. If you're still working on it, you of course can pause it if you're watching this video. And if you're not, I'm sorry, we're just going to keep on moving. But let's see, mx is equal to, okay, so we've got our double integrals. We still have to determine our region. And then it'll be y times x plus y plus 1 dA. Okay, let's do d and d, I guess. So we want to pick our region. One of our regions goes from 0 to 1, right? That's our y. And the other one goes from 0 to 6. That's our x. So I want to put the 0 to 1 for what we'll evaluate first, and that's our y. That's a 0. And then let's do our x. That'll be 0 to 6, because I think the 0 to 1 will be easier to evaluate on the inside. Mx is equal to, so we'll simplify this a little more before we solve it. 0 to 1. xy plus y squared plus y dy dx. And now you have to integrate mx is equal to 0 to 6, integrate the inside with respect to y. So it'll be 1/2 yx squared plus 1/3 y cubed plus 1/2 y squared. Evaluated from 0 to 1, and then we've got a dx. Okay, that 0 to 1 is really easy to evaluate. Well, if mx is equal to 0 to 6, so we'll have 1/2 x squared plus, oh, excuse me, this should be 1/2 y squared on this side right here. That should be 1/2 y squared, if you caught me. Good job. So we'll have just 1/2 x plus, then we'll have 1/3 plus 1/2 value, and then we'll have dx. We can combine those terms a little bit, so we'll have 0 to 6 of 1/2 x plus 1/2 plus 1/3. We'd have to do common denominator to 1/6. So it would be 2 over 6 plus 3 over 6, which would be 5 over 6. And then we'll have dx if I did that. Evaluate the next one. I'll just say the dramatics. So then we'll get 9 plus 5. So we'll get 14 as our mx. And now to find, so with mx, we can find y bar, which is equal to mx over m, which is equal to 14 over 27. Now I challenge you to try my if you want for some extra practice. Remember, it'll just be the region. We'll have an x delta and a dA. If you do that, it's a little bit more of a fraction, so maybe that's why I didn't do this one, but you get 99. It's a bigger number. So then you'll have x bar is equal to my over m. And you'll get 99 over 27. Okay, cool. And then, of course, your center of mass will just be at the coordinates, 99 over 27, comma, 14 over 27. Cool. All right, moving on. My computer's frozen. There we go. Second moments. Okay, so second moment of inertia, it kind of is, I put the definition here because what the second moment of inertia is kind of like eludes a lot of people, and I can't say I've used it a ton in my engineering experience. Definitely used it to describe some dynamics of aircraft in certain aspects, but most of the time it just comes as a specification for the airplane, so I've never had to find it. But it is basically like a geometrical property, and it reflects how like its points are distributed with regard to a certain axis. It's important when you're like stabilizing things on certain axes and stuff like that. I'm sure if you haven't done anything with dynamics, you will probably see the second moment of inertia. But remember, as we talked about in our notes, and of course you can go look back at your notes if you want to solve this, you'll have this is the region y squared delta xy dA. This would be the region x squared xy dA. And if you notice, this is just the first moment, but that term right here is squared. The distance is squared, really. That's all the second moment of inertia is going to be. And then for the iz, it's really just ix plus iy. So you can do that, or it's just the region x squared plus y squared xy dA. So you can see that we're never concerned with volume when we're talking to the second moment. Though we are talking 3D, right? This density is a third dimension. We're just not integrating with 3 dimensions. But yes, awesome. All right, cool. So find IZ for the region between the origin and the Archimedean spiral r is equal to theta, where 0 is less than or equal to theta, which is less than or equal to pi, with a constant density. So the density is constant. That's nice. Can we do symmetry across the axis? Maybe, maybe not. Let's look at it. The shape we might be a little familiar with. I guess I don't need that y much in the positive x. Remember Archimedean spiral, r is equal to theta. Kind of looks like this. We're going 0 to pi, so that's why I only drew half of it. Otherwise the full circle would go all the way around. So this is pi over here, and r is equal to theta, and we kind of just like, looks just like this, right? It's like a big shell, a snail shell or something. Density is equal to 1, so we want to find Iz. It seems like a little tricky because it's in polar, but really it's pretty simple. Iz is equal to, let's use the integral term, remember r, so we have x squared plus y squared delta, I'm just going to not write the dA. Okay, and we can kick this into polar pretty quickly and easily, as long as we remember the specifics, and I'll draw it in green. So we have x squared plus y squared, this is equal to r squared, right? Our density is equal to 1, and then dA is equal to r dr d theta, times r times dr d theta. Cool. And to write our bounds, we never have to decide what order we want to do our bounds in when we're talking about polar coordinates, because it's just dr d theta. So dr, we'll start with d theta on the outside. We're going from 0 to pi. And then for dr, we're just going from 0 to theta. Okay, cool. So now we can solve that pretty simply. Iz is equal to, we've got 0 to pi, 0 to theta. Let's combine our r cubed, dr d theta. So now we go here, we got basically a simple integral. We'll go 0 to pi. Let's integrate with respect to r. It'll be 1/4, r to the 4th, evaluated from 0 to theta. And then we got a d theta on the outside. Then we'll have 0 to pi of, evaluate that, theta to the 4th divided by 4, d theta. Okay, cool. So now we just one-dimensional integral, so we'll have 0 to pi. Well, actually, let's not even write the integral sign because we don't have to simplify anything. We'll integrate that inside term. So theta to the 4th, it'll be 1/5 times theta to the 5th over 4. Evaluated that from 0 to pi. Brings us a really simple one. We'll have theta to the 5th over 20. Divided from 0 to pi. And then we'll get pi to the 5th over 20. And you might have seen this problem before if you were at another session. I might have simplified it for you a little bit so we can just do the multivariable integration. But now you see where it comes from. It's really not that too crazy. We're definitely doing like a crawl, walk, run kind of thing here, where we're starting to slowly ramp you guys up. So yeah, pretty simple, pretty straightforward. That is all I have for you guys. Next session will be on Monday, 5:10 p.m. Another thing is, let me help you. Help me to help you. I put a link in the announcements. It's to a little Google form. You don't have to sign in for the Google form. You don't have to do anything. It's just open text, and you can write whatever you want. If there's something that would help you guys, basically with my sessions, I mean, if you just want to blow off steam for the first 5 minutes and hang out, we can play a game, or if you guys want to see more of a certain type of content, or see more of a certain content on a certain type of platform, if you want more Kahoot, or if you want more OneNote, or if you want more just video of me doing things, whatever helps, you can throw it in that form. It'll really help me kind of start to make these more helpful for you guys, because that's what I'm here to do. That's what I get paid to do, is help you guys get through the course and help you get through right now. So yeah, you can find that in the announcements. And that is all I have. I guess 40 something minutes. That's not too bad. So you guys have an extra 8 minutes to go fill out that link if you want to. That'd be really nice. But yeah, our next session will be 5:10. We'll be talking about more quiz problems. Talking about what we talk about in the Monday lecture. And yeah. All right. You guys have a great afternoon or evening now. And I'll see you on Monday.